Alrighty. Very excitingly, many things come together to give us our first factorization of a matrix. So A can be broken into two triangles. Maybe some row swaps are involved as well, but basically A is interpretable as a triangle times a triangle. Right. So this piece we're going to kind of just go through the process of how this works, and in the following piece we'll explain why. Okay, so some magical things are going to happen. So triangle times triangle, is equals a rectangle. That's our mission for today. And it's our first factorization. You get a t-shirt. There's a little t-shirt cannon, which is over there. And then, as I said, method first. And so the factorization, right? So this is when we take a matrix and we say that show that it can be expressed as a product of two or three matrices. Usually that's the case for factorization, sometimes called decomposition. So we're breaking into pieces that have much more interpretable structures. In this case, it's going to be two triangles. Triangles are nice things. When it comes to linear systems, they're easy to solve. Upper triangular systems, once we have one of those, we solve it with back substitution. If we have a lower triangular system, we will solve it with forward substitution, right? So at least we're using words. At least we've got that. That makes sense. All right. And these multipliers, the LIJs that we constructed a while back, because monks told us to do it, will serve us well. They will do the right thing. Okay. So let's go straight into an example. I'll give you the column picture version. Boom, and we will work through it. It will lack a few aspects that will add some other examples that will kind of fill things out. But 3x3s, we're going to work with those because they're somewhat nutritious. Very nutritious. 1, 2, 3. So this is the column picture, right? So we're adding an accordion, viola. We're always going to have a viola, and a piccolo, let's say, whatever you like. All right, so we want to find, this looks solvable. If you look at this, these three vectors, right, they look like they're pointing in different directions. You probably can't make one out of the other. Can be tricky to see though, but I'm just suggesting it. So this is our B, this is A3, this is A2, A1, this is a 3x3 system. It's really AX equals B, and we have a 3x3, 3x1, and a 3x1. Now we'll get to rectangular systems in the next, after the first exam, right, into the next setting, after the first challenge level into the second stage of the course. This is M by N as always. So yeah, I think the examples today that I'll show you will really be square for a little bit. Okay, off we go, right? So we put this into an augmented matrix story, and that's what we would do. We'd solve it. We're going to step back from that just a little bit. So the normal plan so far, set up this, A, B, right, set up this, it's the augmented matrix, row ups, much pain, suffering, and then we get to U, C, and then back substitution, back sub, and that would give us X. That would be our little flow, right? That's a nice thing to have. Okay, so it would be this. So let's just do row reduction on A, and there's a reason for doing this. So now we'll just focus on reducing A by itself. And eventually we'll see that this is enormously important. A and the transpose, which is the next section. Reducing A by itself. And we'll come back to solving the problem. So what we're doing here is we're breaking A up in a certain way that allows us to adjust for different b's. So that can be a case where you have ax equals b. You know what b is, but b could be changing, right? So someone gives you a new b and you want to solve it again. New b, someone wants to solve it again. That's a lot of work. So we don't want to do row reduction over and over again for each new b. So this is good, very good if b is changed, right? So we're going to know something about a's behavior that allows us to address a new ax equals b, right? So this is our mission. What is our mission? Is this little character here? Pretty much, yeah. That's the plan. Okay, here's our problem. We're off. So we're going to do row reduction again. Good example. So we've got. I'm just going to write down a 1 1 1 1 2 3 1 3 6, and then we'll just do row operations on this. Right, so the first one is row 2 prime. It's pretty easy to see what's going to happen here, right? So this is just row 2 minus, and it's 1 over 1, right? 1 over 1, which amounts to saying we're just subtracting row 1 from row 2. Now, because all these things, so we haven't done this before, this is a bit, getting a bit carried away, but we could do 2 at once, as long as we're not changing anything that's being, right? So we're not using row 2 to do something to row 3. So this is also 1 of 1. So because we're using row 1 to affect row 2 and row 3, we can do them at the same time. That's okay. Right, good. And if there were, if it was an n by n, we could do n minus 1 of these at the same time. In the first column, n minus 2 in the next column. Yes. All right. Boom. First row does not change, so we'll leave that in the right color. The next one, we're subtracting the first row from it. So 1, 2. So right, just subtracting. We're subtracting ones from here and from here across the board because the first row is all ones. Groovy. So then we get a 0, 2, and 5. That is solid, right? And then we do it once more. Again with the ROPs. So this would be, now we're concentrating on this piece. Let me just do that. Ooh. There. And it's going to be row 3. You know what to do. Better than me probably. So row 3 prime is row 3 minus 2 over 1. Right? We're trying to get rid of the 2 that goes on top. We're using the pivot. Pivot is there. Times row 2. And then we'll go back and we'll find all the multipliers and the pivots. We'll pull them out. Good, good, good. So 1, 1, 1, and 0, 1, 2. Those first two rows do not change. We're only changing the last one. And again, we're subtracting 1, 2, multiplied by 2 from 2, 5. Yep. So we get our 0 as desired, and then 5 minus 2 times 2 is 1. All right, so here's our u. Now we're going to reap many benefits from all the good things we have done because we've been good people. We've followed the sacred texts that were first published, I think, in 1969. Okay, so good year. Internet, a few other things. Probably grep. Right, okay. Unix. Okay, so let's see. So, Man on the Moon was a bit of a big deal. Okay. All right, so this is good. We're done. The pivots are not particularly exciting for this one. We'll write them down. They are D1 equals 1. Right, boom, boom, boom. And I'll give you one with better pivots. They're fine pivots, but I'll give you not exciting. I know you like exciting pivots. Now, what were the multipliers that were uncovered? So there's one here. This is L21. This one is L21, L31, which is 1. This one is 1. And here's L32. Right, the 3 and the 2. It was the It's how we got rid of the entry in the third row, second column. And that is a 2. 1, 1, and 2. All right, now of course we've carried this small l with us the whole time, and now I'm saying there's a capital L. So what is going to happen? So so we did these row operations. We've seen now with elimination matrices, let's write that down. So the elimination matrix story, this is where it all comes together. So we had to do row operations, we got to elimination matrices, and we did this thing within inverses for a reason, right? And part of it was to serve our understanding here of elimination matrices being inverted. So we took A and we made U, and U is equal to these row operations acting on A. And the first one is E21. The second one, right, the order is reversed because this one multiplies A first, and then E31 multiplies what's the product, right? So this is the row operations, right? Encoding of our row operations as matrix multiplications. Awesome. Right, very powerful, right? So instead of this little description down here where when we work through it, we've got these little tildes and a little what happened, so we could go back and sort it out. We now have this much stronger piece where it's, okay, we multiply this by this matrix first, and then this one, and we have an equal sign. Right. So U was derived from A. So here's an interesting thing. Right. Monks whisper. Always they whisper a lot. Whisper. Something about Umberto Eco. But they whisper also that invert the EIJs. Okay. So if we inverted them, and we thought about this a little bit, we could put them on the other side. So this whole thing can become, let's peel one off, right? So I'm going to swap this around. Let's put this, let me write it in a way that it's not a disaster. Okay, blue first. So we've got this already. We've got E32, E31, E21 times A, just to try and preserve exactly what we had. So this is the right-hand side from above. Okay, so if we took that, and on the other side we have equals U. Right, this is our left-hand side from above. I'll just swap sides. Now we're going to pre-multiply by inverses of these matrices, and we know that we have to do them in reverse order, right? So to get rid of this character here, we have to multiply by the inverse of its inverse, and then so these ones will be squished, right? They'll become the identity, and then to get rid of the next one, we multiply by E31 minus 1, right? That's this one, and then the last one here, E21 minus 1. So this is going to happen on the same over here as well. There's always a sneaky reason for doing this. So we're peeling all of this stuff off the left-hand side. And everything here, okay, does it make sense? I'll move that equal sign. I'll move this here into here, equals this. So this of course is a 3 by 3. This works for arbitrary sizes. Everything here, all of these pieces here, this just becomes the identity, right? Each elimination matrix and its inverse gets matched up. They become the identity. They get absorbed. Identity times any matrix is that matrix. So this is the identity times A, So the whole thing gives us A equals essentially the row operations acting in reverse. Should make sense, right? So we did these row operations to go from A to U. Now we're going to do them in reverse to go back to A. So these are the row operations in reverse. We'll say this again, but U has relatively simple rows because it's upper triangular. And then A is the potentially very messy, complicated thing we started with. This is now telling us how to combine U's rows to make A. So let me write that in words. It tells us how. Now, it could be a horrible mess, right? I mean, there are 3 row operations here. That's true for a 3 by 3. We figured this out in class the other day, right? So it's 1 plus 2 plus 3. So it's not a great thing. It's n times n minus 1 over 2, which is growing like n squared. How many row operations we need? It tells us how to combine rows of U to make rows of A. And the rows of U, let me just sort of accentuate that. These are, I'm going to move this over here. So I'm going to highlight it. So rows of, these are simple-ish, right? They are, right, they're simple-ish to make these rows of A. All right, well, we haven't seen this yet, but these things are going to combine themselves. All right, so we will see. Let's get this again. So this is upper triangular. And what we'll see is all of this stuff, we're not quite there yet, turns out to make a nice, we can always figure out what that product is. It will be lower triangular. So this is amazingly, we see this. A is equal to LU, where this one is going to be of this form. 1, 1, 1. And this is just for a 3 by 3 square matrix. And we'll see L2, 1. So we'll see, because we'll show it just sort of for this example, and then we'll show it's true in general. L3, 1, L3, 2. And these are going to be pluses, pluses, pluses. This is, you know what, I should do that too. So U itself is, U has D1, D2, it has the pivots here. It definitely has zeros here, and it has something here, something here, something here. And we did figure them out, right? So it's 1, 1, 1, 2. So I guess I could write that. But in general, this is in general what it is. Upper triangular. Upper triangular. And incredibly, this will be lower triangular. So lower and upper triangular, what does it mean? So lower means the stuff, right? The potentially stuff below and including the main diagonal. But the important thing is really it means that there's zeros in the upper part, and upper triangular means the opposite. So this is actually true for any rectangular matrix. We'll get to the shape. It's not here. This is actually, in general, this is an m by n. Very importantly, this is m by m. This is square. M by m. And this one will be m by n. So U and A are the same shape, right? So it could be rectangle equals this lower triangular thing like this times another rectangle, which will be have zeros down here and maybe some stuff in here. All right. Let's leave that for a second. let's finish our story here. So I want to take this statement here. Let me get it. I want to take this. Let's plonk it down here, and let's work for. Okay, let's work with this. So I'm going to clean this up a little bit. Okay. Now, I've said a few things about this. I've made some claims about it. First of all, these are simple. So from the previous piece, we know, back a few, we know these are simple. So that's exciting, right? So if we did all this before. So E3, 1, so an example would be, so E2, 1, right, the basic one, the first one I should say, equals, and in this case it's 3 by 3, so let's keep it like that. So it's 1, 1, 1, and L2, 1. This is how we structured things. The inverse of this, so what's going on? This says keep the first, if you multiply this elimination matrix onto something, it says keep the first row as it is, keep the third row as it is, and then for the second row, this is our row operation, right? This encodes row 2 prime equals row 2 minus L2, 1 times row 1. And to undo that, we'll want to say row 2 prime is row 2 plus L2, 1, row 1. Right, so if you do either order of these for multiplications, they'll clean each other up. So this is going to be plus L2, 1, 1, 0, 0, 0, 1. So we just flip the right. Okay, so there's a number of observations here. So all right, so recall, right? Really? I guess that's a fair way to say it. So big deals. So 1. So the E matrices, Eij minus 1 is Eij with off diagonal, with single off diagonal flipped, element flipped. Flipped in sign, right? Very simple. So that's good because we've worked at this. Finding inverses is again a whole bunch of other row operations. So it would become kind of an inception situation. But that's not what's happening. We know how to do these easily. They're all lower triangular. So the Eij's and their inverses, Eij minus 1s, are all lower triangular. And that's because, right, so the L's only appear here and here and here. And when we do Gauss-Jordan, we actually put them up here, but that's not what we're doing. We're just doing Gaussian elimination. It's because we only use rows above to clean up rows below. And when we flip to just starting to do Gauss-Jordan, which we do for finding inverses, we start to use the rows below. But to start with, to make an upper triangular matrix U, yeah, got it. We use rows above, right? We use the first row to clean up the second, third, fourth, all the way down, and then we use the second row to clean up the rest of them. Good. So that's a good thing. They're all lower triangular. They're very, very simple. They mostly look like the identity matrix. So let me say that. 3, right? Eij is the identity with Lij replacing the 0 in the in ij position. Right, so this is the identity matrix with minus L2, 1 in the 2, 1, right, second row, first column. Yes, good. So that's good. And now, and I'm just going to write this. We'll do one little multiplication here. So we know what these inverses are. All right. So this is going to be 4. Remarkable. There's a whole reason for it, of course, but let's do this. So it's going to be E21 minus 1, E31 minus 1, right? This is the stuff we're multiplying. Let's write it out in this case. Good to do. So this is going to be, all of them will look like, as we've said, and I'm just going to put in that they all look like the identity matrix with one piece change. And these are the inverses, so we have pluses in them, right? 1, 1, because we were told to put minus signs in. And now we are getting the benefit, plus L31 plus L32. So let's multiply them out. We'll just do the first two to start with. And I want to use it in this way. This just says first row stays the same, second row stays the same when we multiply the next piece. It's a very powerful way to think about these things, right? So the first row here is 1, 0, 0, right? So I'm just keeping this row. And the last row is this, L31, 0, 1. What does this say? So this says take the new row 2 is the old row 2, that's this one, plus L21 times the first one. So we're taking the old one, it's 0, 1, 0, and we're adding L21 of the first one. That only means this gets multiplied by L21, and we add it to 0, right? L21 times 1 plus 0. L21 times 0 plus 1 is 1, and then L21, they're all zeros, so that stays as 0. And then we still have this piece on the end. L32, 1. So let's multiply that together. See what happens. So again, the top, this says take the first row of the next matrix, and that's all we want for the new first row. This says, again, take L21 times first row and add it to the second row for your new second row. And this says, for your new third row, take the old one and add L31 times the first one. Leave some of that in there. Okay, so new row doesn't, the first row doesn't change. We have L21, so it's a very similar business there. 1, 0. And then we take L31 times the first row. That just really gives us this piece. Adds it to the 0. And it should look pretty clean what's going on. So look at that, that's great, that's fantastic. So it's an upper triangular matrix, and it's very simple. Right, the L's, this doesn't work. Matrix multiplication is usually a complete mess, but there's some beautiful, simple aspects to row operations that we get to profit from here, and we will call this L. L always has 1s on the diagonal. This is a bit of a funny example because the pivots are all 1, so it looks like that might be true of you, but it's not generally. 1's on the diagonal. I think I will add another example that will help with that. All right, so what have we done? We've shown that, I'm going to go back here and call this L. This is what will become L. So A is LU. So we can do this decomposition or factorization. And it's as if we don't have to, we really don't have to do the multiplication. You can just go and just dump in the multipliers. So for our example, so back to the example. What do we have? Our multipliers were 1, 1, and 2. Right. L, for us is going to be, looks like the identity matrix, and then we're going to just plug in the multipliers in the right spots. 1, 1, and 2. And you can go and check that this works, right? That this L times the U that we have, this blob, is what we want. So let me, so we have, what's our A again? Our A was 1, 1, 1, 1, 2, 3, 1, 5, 6, 1, 3, 6. And now that equals this L times U. L times U, which equals 1, 1, 1, so 0, times U. And in this case, U was, there's a special thing that's happened here. I'll come back to it. 0, 0, 1. So just to annotate these things, L21 is here, L31 is here, L32 is here, pivot 1 is here, pivot 2 is here. They're not complicated pivots. All right, so we've replaced A, potentially a rectangular matrix, with two simpler matrices, lots of zeros in them. And the zeros mean that we can solve an AX equals B problem. And you are psyched because that's what you've been wanting to do all day, I'm sure. Yeah. All right, so let's solve this, and I'll come back and explain why this works, all the time in a little bit. All right, let's just finish. So let's solve AX equals B if for the case that we had, right, we had this B is 5. We haven't touched B yet. Right. So now it becomes, right, so I'm going to write it, let me write it, I suppose. So now, yeah, so we now solve this by solving two triangular systems. And these are easy because they're triangular systems. So let's get them in order. Right, so the first one, so we're going to just replace A. So we have L, U, X equals 5, 7, and 11. Right, equals B. That's our B. So what we're going to do is we're going to call, so if you remember, our notation was that this is what we called C. Ux equals C, right? U x equals C from before. Wow. This thing is confused. Okay, so good. If that's true, let's just rewrite it. So now we've got L times C equals 5, 7, and 11. And the thing about this, maybe I haven't said this properly, is that we know what L is, right? We don't know what C is, and we know what this beast is. Oh, this is B. So this is an AX equals B problem, but triangular. So we would use, let's put things back in. So it's 1, 1, 1, 1, 2, 0, 0. We write it out just as we did with back substitution. This is going to be C1, C2, C3 in this case, equals 5, 7, 11. And we solve by forward substitution. It's lower triangular, forward substitution. Yes, great. So let's do it. So we start at the top and work our way down. So row 1, in this case, will just tell us that, right, we take this inner product it just says C1 equals 5. Row 2 tells us that C1 is C1 plus C2, and of course we have a 0, that's our benefit, plus C2 equals 7. And we have C1 already, that's a 5, so that's going to give us C2 equals 2. Yep. And then row 3 has 3 pieces in it. C1, 2C2, C1 plus 2C2 plus C3, all of that equals 11. Let's put in the pieces. So this is a 5. All right, we've got a 5 here. We have a C2 we know is 2, so we have that here. So it's 5 plus 4. Right, and then take it to the other side. So this will give us C3 equals 2. So our C vector is, right, that was forward substitution, 5, 7, and 2. Right, now solve ux equals c. And so now we're back to where we've been many times, and this is with back substitution. Good. And because of our step that we've just taken, so we know u and we know c when we're trying to find x. Yep, groovy. So 1, 1, 1, 1, 1, 2, that's u. This times x1, x2, x3 equals c, and c is, which we just got, it's just 5, it's, oh, I made a mistake here. This is 5, right, 5, 2, 2. Good. So back substitution, so now we go upwards. The last, so row 3 will give us that x3 equals 2. Row 2 gives us that x1 plus, x2 plus 2x3 equals 2. And then row 1 gives us that x1 plus x2 plus x3 equals 5. And as we go through these things, right, so we've got x3 is 2, so this is a 2. This gives us that x2 equals, right, so there's a 4, so put it over here, so it's minus 2. I got the right thing. I think so. Yep. And then this will be a 2 here, this will be a minus 2 here, which gives us simply that x3 equals 5. x1 equals 5. Yes, that's where it can go wrong. Okay, good. So final solution is here. Finally, we reached the solution, and that is 5 minus 2, 2. Right, we had to solve 2 equations, and you can go and check that this works, and you should do that. You should check. You should always check. I'll cavalierly say this is correct. So done. So the benefit here is someone hands you a new B. Well, I mean, apart from understanding this is really what Gaussian elimination does. Okay. Okay. Right. If you want to swap in a new B here, just do it, and you go back here and you'll solve this triangular system, get an answer, and then solve this triangular system. No more row reduction, right? So the row reduction is done. Big deal. Big deal. Swap B, easy to solve. Row reduction is, so that's if you have an A that's going to be preserved, right? Row reduction is done once. It's done once and is encoded in L and U. That is pretty awesome. Lots of good things there. That's good things, good things. We had a bit of a funny example, I guess, because of the pivots. I'm going to give you, should I give you this one? I have an example here, which is okay. I'm in love with it. Just to finish all of this off. Okay, so we're not going to work through it. So extra pieces. So let's just make an observation is that I think I should have noted back here. Yeah, let's look at L and U here. They are what we'll call transposes of each other, right? So if you take L and flip it across its diagonal like this, then it's a mirror image of U. And if we go back to A and look at A, it's a mirror image of itself as well. So A is special. Our A was special because A equals A transpose. And that led to what there's it's not quite this in the always true, but L and U are transposes. Now it can't generally be true because the U should has pivots on its diagonal. L has ones on its diagonal of each other. But only because D1 equals D2 equals D3 equals 1. Right? So normally they should be different. Here's how we, so that's one little piece. Here's what we, so this is so LU factorization, that's what it's called. I mean, it's a terrible branding. And then incredibly, there was also LDU, but it's a different U. So let's look at this. This is kind of wrong. So also very, very useful. We separate out the, and you'll see this over and over again with our factorizations. It's often nice to put them into 3 vectors. So separate out the pivots, like make it really clear. So let's take an example. Let's say we have this one, 2, 1, 3, 2, 0, 0, 4, 3, 13. So this is A, and a little more space. Yeah, I'm going to move this across. Okay, so that, we're not going to do this factorization, but here's what it is. So again, 1, 1, 1, always ones, right? 1, 2, minus 1. These are always ones. And these aren't rectangular, but this is an m by n, and this is always an m by m square. A and U are the things that look like each other. Very important to remember. In shape, they have the same shape. So 2, 1, 3, let's say we have this, and 0, well, this is what you would find, minus 3, 0, 0, 4. So the pivots are here. Let's just identify everything. We have L21 equals 1. That's this character. L31 is 2. L32 is minus 1 from the L matrix. Right, let me just say this is L. And of course, this is U. Now, a very odd thing that people will do because of notation. Either you're doing LU or LDU. You sort of just say that. So the pivots are D1 equals 2, D2 equals -1, and D3 equals 4. So this is an alternate factorization. And this is, U is different. U is different. Oh, this is terrible. Would be, so everything looks the same. We have the same L, 1, 1, 1, 1, 2, -1, 0, 0, 0. We're going to pull out D. We're going to make now this one is going to be m by m. This one is also going to be m by m squared. And it's going to have the pivots sitting there on the diagonal. And if we go through, we can say, well, if we've pulled out a pivot from the first row and the second row and the third row, we're dividing through, right? We're dividing through. So if we divide the first row by 2, we get this. The second row gets divided by -1, so it's just multiply by -1, and the last one goes to 1. So this is also a nice factorization U. Right. LDU, A equals LDU. We'll come back to this. Let me just write it here. If A equals A transpose, this is next. I know it's a little crazy. Then A equals L D L transpose. And you'll see some more goodness about that. This is equal to U. So it's a bad sort of notation issue. LU, the U in LU is not equal to the U in necessarily. Only if all the pivots are 1. So you just have to know which one you're doing. You have to state which one you're doing from the, just so simply state must. Right, so we must state which game we're playing. Which factorization, which form, oh dear, form we're using, okay? From the start, okay. That's pretty good. It's a fairly amazing result. You can do this with everything. I think one important thing just to finish with here is we haven't talked about row swaps. Last thing is row swaps. And the way we do this is we figure out computationally how to do them all at the start. So we do at the start. So we fix A up, if you like. So that's going to look like this. Permutation of A equals LU, or permutation of A equals LDU. This is possible for every A matrix. Possible for every, now some factorizations won't work, but possible for every factorization, every matrix A. We can always do this factorization. So that's a big deal. That's your first factorization. It's a pretty workmanlike one in that it kind of just gets a job done. It's not beautiful. We will see very beautiful ones later on, kind of exquisite ones. So, but it should be hopefully satisfying. The next piece, I'll explain why this bananas thing is always true here. Thank you.